We next look at some other things that differ from relativistic kinematics compared to classical kinematics. Now, all of these changes, they don't mean what I taught you earlier, what you learned last semester is wrong necessarily. When we talked about momentum, for instance, in this section, we learned that momentum, classically, was the mass of the object times the object velocity. Last semester was P is m times v, but in this chapter, we're using u to represent the speed of the object, not v. So it's just momentum is mass times velocity. And here u represents the relativistic velocity. So classically, this is our equation. But it actually doesn't quite work. If you have an object traveling close to the speed of light, what we find out is relativistically the momentum is mass times velocity times that Lorentz vector, gamma. Remembering that gamma is 1 over the square root of 1 minus v squared over c squared. Remember, gamma goes between, gamma can be as little as 1, but it has to be greater or equal to 1, and it has to be less than infinity, depending on the speed. Or actually, this isn't v then, my apologies, this would be u, because we're measuring the speed as u in those other equations. So, at low speed, gamma is close to 1, and these two equations are basically identical. So for collisions on the highway or collisions in the lab, we're not having things travel at relativistic near the speed of light in our laboratory environment. So we don't have to worry about these difference between the relativistic and the relativistic and classical versions of this equation. The relativistic becomes the classical version at low speeds. This is called correspondence principle. Now, as the speed approaches the speed of light, gamma approaches infinity. So what happens is the momentum, the closer and closer a particle's speed gets to the speed of light, the more rapidly the momentum increases. So here, example, this is the momentum of an object as a function of speed, a u. This is the speed of light here, this dotted line. That's the fastest an object can go. Classically, this equation will give you the blue line, where the momentum would just reach some maximum, right? If you know what the mass of the object is and you plug in the speed of light, that tells you the classical limit of an object's momentum. But that's wrong. As the object approaches the speed of light, the momentum goes to infinity. It asymptotically approaches infinity. So you get a different result for objects traveling close to the speed of light. Now, again, in collisions of particles in the air in this room, things like that, those are not relativistic collisions. But if you go to a particle accelerator and accelerate a proton to near the speed of light and smash it into other protons, then you have to worry about relativistic momentum. However, relativistic momentum in collisions is conserved in all reference frames, just like classical momentum is conserved in collisions. If you have no external forces, then the change in momentum of a system is 0. The momentum has to stay the same, which means the momentum before the system collided and the momentum after the system collided have to equal one another. That's conservation of momentum. Relativistic momentum must also be conserved in all reference frames. Now what about this m, this mass your book talks about a bit? Mass measured here, what is the mass of an object? The mass of the object, again, you can think of it as the amount of stuff the object has. It's not really a weight is a force, but you can use weight to determine what an object's mass is. Mass, in these equations, is what's called the rest mass of an object. It's the mass measured for an object in the same reference frame as the observer. So if I take an object and place it on the scale and do mass measurements, if I use gravity to weigh it, or I measure its mass through changes in momentum, or however I measure the mass, it's the mass measured in the reference frame of the object. So I'm not traveling, I have no velocity with respect to the object. That's called the rest mass. Now your book talks about, in earlier books, or one way to think about this, and how I was taught to think about this, was if you combine these two terms, gamma and m, what you'll notice is it looks like the mass increases with gamma. Gamma changes with speed. So the speed increases, gamma gets bigger, it approaches infinity. So it's as if the object gets more massive. So it's as if the momentum increases dramatically because the object gains mass as it approaches the speed of light. Now this is an old way of thinking about things, and you'll still find books that talk about it that way. And conceptually it might be useful to think about it that way. But realize that it's an outdated method. The mass we see here is the rest mass of the object. It's the mass of the object in our reference frame, or in the observer's reference frame. So while it might appear mass does increase as an object moves from that relationship, we don't care about that. We care about what the rest mass of the object is. What is the mass of the object in our reference frame? So this talks about relativistic momentum. We talked about energy last semester too, right? In collisions, you can have conservation of energy and conservation of momentum. In elastic collisions, energy is conserved as well. Well, what about kinetic energy for relativity? Let's look at that next.